Alright, welcome back everybody. In this video we're going to look at the definite integral and area, and the connection between the value of the definite integral and area. We start here with a basic definition of the area under the curve as a definite integral. If we have a function that is non-negative and integrable over a closed interval, then the area under the curve is just equal to the value of the definite integral from one end point of the interval to the other. Alright, let's look at an example here. And it says here we can calculate areas using integrals, and we can calculate integrals using areas. So let's look here in example 1. We're going to evaluate the integral from -3 to 3 of the square root of 9 minus x squared dx by using geometric properties. And based on what we know about integrals so far, we don't really know how to calculate the value of this integral. But when we look at the curve, we can see that what we have here is we have a semicircle with a radius of 3. And so in order to find the value of the integral, we can find the area of this semicircle. And so the area of the circle is going to be pi times the radius squared. The radius is 3. And since it's a semicircle, the area is going to be half of that. And therefore the value of this integral is going to be 9 pi over 2. And that's the value of the integral from -3 to 3 of the square root of 9 minus x squared, using the connection between integral and area. Alright. Next, what we see boxed here, when we have a function that's non-positive, the integral finds the area between the curve and the x-axis, but treats it as negative value. So if a function is less than or equal to 0 on an entire interval, then the area of that is just going to be the opposite of the value of the integral. So if I took the integral of this interval where it's all below the axis, it's going to return a negative value, and the absolute value of that value is equal to the area of the region. And using this, we can then deal with relating the integral and area for any function, whether it's positive or not positive or whatever. By using this relationship, the integral from a to b of a function is equal to whatever area is above the x-axis minus whatever area is below the x-axis. And we're going to use that here in example 2. In example 2, it says to use the graph of the integrand and area to find the value of the integral from -2 to 3 of the absolute value of x minus 1 plus 1. Alright, and this is going to be a v-shaped absolute value with a vertex at 1, 1. And I'm just going to hand draw in that. And there's what our curve looks like. And we're finding the integral of this from -2 to 3. So let's put those boundaries in there. Here's -2. Here's 3. Oh, oops. Oh, darn it. This was one where there was a typo in the equation. I'm sorry. I'm going to fix this, and because I wanted to illustrate what we're talking about here. We're actually going to find the integral from -2 to 3 of the absolute value of x minus 1 minus 1, which has its vertex at 1, -1. Because this is more of an illustration of what we're talking about in this context. Alright, and we're going to integrate that from -2, it's right here, to +3, which is right here. And so what we have when we do this is we have, because of our axis, let me darken the axis here a little bit, there's the axis. We have some area above in here, and some area below, and some area above. And so to find the value of this integral, I'm going to take the area above, which I've got a triangle with base of 2 and height of 2, and I have another triangle with base of 1 and height of 1. That's all the positive areas. And then below the axis, we see here a triangle with a base of 2 and a height of 1. And so we're going to subtract that away, the area, base of 2, height of 1. And when I do all these calculations, that's 2 plus 1/2 minus 1. We get that the value of this integral is going to be 3/2, or 1.5. And it's as simple as that. Find the area that's above the axis, subtract away the area that's below the axis. All right. On to example 3. This is a free response question from the 2014 AP Calculus AB exam. We see a graph of a function f, and we're told that the function f is defined on the closed interval from -5 to 4. It consists of 3 line segments and is shown in the figure above. G is the function g of x equals the integral from -3 to 3, or the integral from -3 to x of f of t dt. And here we're supposed to find g of 3. So we start by, putting that into the notation that we're provided. G of 3, because of this right here, is equal to the integral from -3 to 3 of our function f of t. And so it's going to be based off of the area between this curve that we're presented and the axis, from -3, which is at this point right here, to +3, which is at this point right here. And so in order to find the value of that integral, we're going to take all of the area above the axis and count that as positive value towards the integral. And we're going to take all of the area below the axis and count that as negative on the interval. I actually need to erase this so that I've got a better view of where that curve actually is. Because I went a little bit too... Okay, and so to find this area, we have a triangle that is entirely above the axis. That's going to be treated as positive value when calculating the integral. And this triangle has a base of 1, 2, 3, 4, 5, and a height of 1, 2, 3, 4. So the area of that's going to be that. And then the fuchsia, whatever color that is, triangle below the axis, counts as negative value towards the value of the integral. So we're going to subtract that away. It's a triangle with a base of 1 and a height of 2. And then I'm going to go ahead and do those calculations, and that gives me 10 minus 1. And so the value of this g of 3 is going to be 9. All right. Let's do another free response question from an old AP exam here. Example 4 is free response question number 3 from the 2012 AP Calculus AB exam. We've got 3 line segments and a semicircle centered at the origin in the graph. And we're supposed to find 2 things here in this problem. We're supposed to find the value of g of 2 and the value of g of -2. So let's start with g of 2. G of 2 is equal to the integral from 1 to 2 of f of t dt. And we got that simply by substituting 2 into this function here for x. And so we want the integral from 1 to 2, which is going to be based on the area from x equals 1 to x equals 2. It's just going to be based off of the area of that. Now, since that is all below the axis, I'm going to take that and make it negative. And then the area of that region is 1/2 times the base, which is 1 unit, and the height, which is 1/2 unit. And so we end up with g of 2 being -1/4. And then I'm going to do something very similar for g of -2. We're going to just set this up as the integral from 1 to -2 of f of t dt. Now we've already talked about some integral properties, and we're going to use those here because we don't want to accumulate integrals from a bigger value to a smaller value. And one of the integral properties that we've talked about is that we can just pull a negative sign out in front of that integral and switch the limits of integration. So this is going to be equal to the opposite of the integral from -2 to 1 of f of t dt. And so now I'm going to calculate the area of that. I'm going to go back up to my curve here, and we're going to find the integral from -2 to 1. And so we start at -2 and go over to 1, and so we've got this positive area and this negative area in the semicircle. And so I'm going to keep that negative sign out in front. Now the positive area comes from a triangle with a base of 1 and a height of 3. So we've got 1/2 times 1 times 3. And the negative area that we're subtracting away comes from the semicircle with a radius of 1. So that's 1/2 times pi r squared. And we subtracted that away in here because it's area that's below the axis in the picture. And now we just need to calculate the value of this. And that's negative times 3/2 minus pi over 2. And so this is going to be pi over 2 minus 3/2. And that's going to be the value of that integral. Alright, that's where we're going to stop for this video. We'll come back next time and look at the rest of this lesson. See you guys then. Have a great rest of your day.